Hey everyone, welcome back. Today we are diving into Bloom filters, a probabilistic data structure used to efficiently check whether an element might be in set or is definitely not in that set. If you want to save space and handle massive data sets, Bloom filters might be just what you need. So, let's see how it works. As always, we answer the what question, okay? And in this what question, we're trying to think about what is exactly the Bloom filters. And we can think about the Bloom filters like a Bloom filter is a data structure that answers set membership queries with two possible outcomes. Number one, the item is definitely in not in the set. Number two, the item is possibly in the set. Okay, so two things. The item definitely is not in the set. Number two, the item is possibly in the set. Okay, it uses less space than other structures like hash sets, but it can produce false positives where it says an item might be in the set where it isn't actually in the set. The trade-offs is a tiny possibility of error or for a big gain in memory efficiency. Okay, let's try to understand on how it works. So we have this example, so we can look at this example to understand how exactly it works. Okay, so think of we have a bit array here, okay? And think of bit array as efficient storage for possible membership flags. And each hash function provides a unique way to map items to bit position, okay? So, yeah, step two, we have hash element. Yeah, number two, we add an element. So, for example, we hash the element when you add a new item. Okay, you feed it into like each of the khash functions, and after that we have set bits. So each hash function outputs an index within the bit array. Set the bits at these key positions to one, for example. So as you can see here, the functions are sending all the index, and each one we set it to one, as you can see here. Okay, so that's it. Like the item is now marked in the Bloom filter via these multiple bits. Okay, let's try to understand how this works. So again, we said we it happens in two steps. First, we hash the element. Like when you add a new item, you feed it into each of the k hash functions. So we have here two hash functions. Okay, these hash functions. And number two, each hash function will output an index within the bit array. Set the bits at these key positions to one. So again, so the hash function the hash function will output the index, and we set each index at one. As you can see, each one it will be equals one. And yeah, that's it. But how the query works, why it is that important? If you want to understand how the query works in three steps. First step, hash again, sorry. Like for a lookup, you run the same key hash functions on the item. Number two, you check bits, like if any of the bits at the resulting position are zero, the item is definitely not in the set. Number three, we have some possible matches. Like if all of these bits are one, then the item is possibly in that set, or we have a false positive. So no bit is ever turned back to zero. So false negatives, like saying definitely not in the set for an item that actually is, are near impossible. Not are near impossible, it's actually impossible. Okay, so let's try to next talk about why we use the Bloom filters. Why that? So there are three things. First, space efficiency. Bloom filters require far less memory than a classic hash set, or list the same data. Okay. Number two, fast lookups. Checking membership or adding an element only involves a new hash computations and bit checks. Number three, no false negatives. Like you will never accidentally discard an item that is in that set. There are they are used in many applications like caches to check if an item might be in the cache, databases as well, like a quick existent check and network filtering system. Okay, let's talk about like the trade-offs. Okay, if you want to talk about the trade-offs, there are three things, not four, three things. First, we have false positives. Like the filter can sometimes say item X might be here when it is not. Number two, no removal, like no removal by default. Like standard Bloom filters don't directly support removing items without risking false negatives. Number three, tuning. Choosing m bit array size, for example, and k number of hash functions requires balancing error rate with space usage. For many use cases, these trade-offs are acceptable, especially when memory or speed it is a premium, and a small change of false positive doesn't break the system and doesn't affect that much. Yeah, I guess we can wrap everything up now. Yeah, that's Bloom filter in a nutshell. They are a clever probabilistic data structure for quick membership checks using minimal storage and offering no false negatives, but with the trade-off of possible false positive. If you found this video useful, hit like, subscribe, and let me know in the comment section if you have used Bloom filter in your project. Until next time, keep optimizing your data structure, and bye guys.